button. There we go. So yeah, you guys have a quiz today. If you haven't taken that, make sure you do so by 11:59 Eastern Standard Time. Well, you have what, like 40 minutes to take the quiz, right? So you really should start a bit earlier than that. But yeah, so the quiz covers really 11.10 and 11.11 are the focus. But of course, right, it may cover other sections because there's a lot of convergence, divergence stuff that you may need to use, like the ratio test, for instance, on. Also related to that, I have here kind of on our D2L page, and let me show you maybe how to get to this. So if I was at the course home, really what I would want to do is go over to the content, and we'll probably be making a nice link to all of this here in the near future as well. But on the left-hand side, you can see that under week 14, we of course will have some lessons and stuff like this. I'm going to be posting the notes for next week's class here under the week 14 video lessons. And Monday's class will be a review class, so I'm going to prepare some problems and stuff like this. And then the TA should be running like mini recitations on that Tuesday, right, to answer any questions. And of course, you can post them to Piazza and all that sort of stuff as well. But exam 2 is really what I wanted to talk about here. So first of all, up here at the top, we have important info about exam 2. And so I'll click on this and kind of go through a few things. But you'll also see that we have the formula sheet, some old Math 133 exam 2s. So this just takes us to the uniform site. And so what kind of questions have been asked in the past. And then we have some nice kind of review sheets and stuff like this that various instructors have contributed. But I wanted to click on here, actually right before our class today, we got some more kind of nice information that we can share about the exam. Of course, so it's 90-minute long exam, similar to, the structure of the original exam 1 and what we had planned for exam 2 and all that sort of stuff. You do have a long period in order to take the exam, but it's not all day. So this is an important distinction between the quizzes versus the exams. You have between 8 a.m. Eastern Standard Time and to 7 p.m. Eastern Standard Time. So make sure if you wait and you think you can take it, up until like 11:59, you'll be quite sad. So please make sure you mark your calendars and that you take it in that time frame. It does cover all of Chapter 11. So this Chapter 10 stuff, decided to kind of have this on the final exam, most certainly, but only Chapter 11 stuff, we found that's quite enough for exam 2. So we'll have that. And yeah, like I said, next Monday we'll have a review session as well. As far as the question structure, this is kind of the new bit that we got to add, just before class here. So there'll be kind of 5 standard web work style questions. So these are, questions that are basically they're basically like the standard response, as close as you can get to that with an online computer system. And so they're, web work problems, and maybe you get some partial credit if you can make it. There's various answer boxes and opportunities to get some partial credit. So that's going to be 40 points total. There's some true and false questions, some multiple choice, and some that only just want the answers. So you can call those fill in the blank or answer only, things like this. And so that's kind of the distribution as far as the exam goes. And we've kind of taken it, and we were happy with the time and all that sort of stuff. So 90 minutes should be enough to do these questions. Similar to the quiz, right? You get to take it once. You get 2 grading submissions. So if you, have some mistake, and you can go and find it, and you can get it correct the second time, right? It's the highest of the 2 grading submissions that get recorded. Okay, I see. Will there still be office hours the day of the exam? So this is one of the questions that's asked here. Office hours, I mean, I'm not canceling my office hours or anything like this. I have them right now by appointment, but we're not planning on running one of these class sessions on the day of the exam, just because there's a bunch of really wonky things that can happen. But because the exam will be open all day Wednesday, we're not going to be holding one of these live sessions on that Wednesday. But we will have a review session on Monday, and there'll be opportunities on Tuesday, basically like with the recitations with the recitation instructors to help you guys out. Anything else I should be mentioning or thinking about, Alec?
Well, I would just say for the office hours on the day of the exam, I normally, get on Piazza and answer all kinds of questions on there. But with the exam being open, I don't think I can really do that. So I think I would probably say I probably won't have office hours on that Wednesday.
Okay. Yeah, that makes sense. Kind of things more or less, shut down while the assessments are open. It's very similar to the quizzes and stuff like this.
Right.
I also see in the chat, will it tell us what pages we have an error on? And so yes, the exam is very much, we're basically using the same settings as the quiz. Of course, there's a few more questions and things like this, but it'll, when you do that first submission, in the top right-hand corner or so, it'll say, page 1, 100%, page 2, 50%, stuff like this. So it'll tell you what pages errors are on, but it won't tell you what specific subparts or anything like this have errors. All right, anything else? I see another question just popped in here. Will it tell you your exam scored immediately after submission, or will we have to wait for them to be released? So yes, it'll tell you the exam score, just like the quizzes do. It'll tell you what your score is right after the submission. So I'll go ahead and mark that. Okay, I think that's more or less all of the administrative stuff or things that people should be thinking about. There's a few other questions we'll type out answers to here. I guess one more just came in. We'll go ahead and answer that. Is there a way that I can see my quiz again on WebWork? So yes, on WebWork, and sadly I don't have it pulled up here. It'll take me a second in order to get this. I don't have any old quizzes maybe. So you probably don't see this page ever. So I'm going to go ahead and log into a WebWork. And down at the bottom, it has these previously generated versions of time sets. So that folder right there has any of your time sets, the actual versions and the questions that you had specifically. So I have some like practice exams and stuff like this. So you can go in and see what you got right and wrong there. Okay, one last chance. Any other questions that we should be thinking about, Alec, or answering live?
Well, I just answered one of them here, but one that I wasn't positive about either. Somebody said, will people register with the RCPD still get extra time?
Yes, yep, we have an option to do that. So we have been. Likewise for the quizzes. Okay, well, with that, why don't we go ahead and start in on 10.3. So remember, 10.1 was about parameterizations, right, and how to parameterize curves. In 10.3, we're talking about yet another different type of coordinate system. So kind of what we've known and loved for a long time is the Cartesian coordinate system. Also, this is sometimes called the rectangular coordinate system, where we have a lot of X's and Y's. And so last time we talked about how can we add in this t variable, which we called a parameter, this new independent variable thing. And now we're going to talk about another type of coordinate system. And again, this will kind of lead into Calculus 3 very nicely. So this is one thing that certainly does get expanded on. But we want to learn how to do calculus in other coordinate systems. So in particular, another popular one is polar coordinates. So, right, and we talked a little bit about in the videos how instead of specifying an XY pair, we could specify how much you turn, maybe counterclockwise from the positive x-axis, and then how many steps you take out. So what is your kind of radius to some extent? And so, of course, we wonder, well, how can you relate this new coordinate system to what we know and love? And so we have a bunch of equations here. These ones right here are very good at taking the Cartesian coordinate system and turning it into the polar coordinate system. So here's how you could get r. And then you also have, again, Cartesian. If you have an x and a y point, you can figure out what the theta is. You would just need to apply a tangent inverse on both sides. On the other hand, if you're interested in, right, you already have maybe your polar coordinate system and you have an r and a theta, right, you could plug these in and you could get y and x using these equations here. And these are things that you really don't have to memorize so much. If you just use this picture up above here, right, you can very clearly see, for instance, the Pythagorean theorem gives you r squared x squared plus y squared equals r squared. So this is just using the Pythagorean theorem, for instance. Or if you use the whole sine is equal to opposite over hypotenuse, or cosine is adjacent over hypotenuse, right? These formulas just kind of fall out of that. So these aren't things that you really have to have super memorized. And of course, right, with our quizzes and exams being open book and everything like this, maybe you're not so worried about this anymore anyway, but these are common questions that I used to get. So maybe I'm just used to answering them. We start off by plotting a few points, getting the hang of things in these polar coordinate systems. Then we move on, we do some conversions and all this sort of stuff, kind of practice with these. And then we get into sketching full-on polar curves. So we have an equation now giving in polar format, and we sketch the curve and maybe identify it, things like this. So we can graph it, we can say what geometric figure it is, and in some of them we can even transform it into Cartesian equations, and that's nice to double check our work. And so we do that a few times. And this is really what our class today is going to be expanding on. We do get 2 days dedicated to 10.3. So that's where we'll actually get into some of the stuff about like tangent lines and things like this. But for today, we're just going to focus on graphing in polar coordinates. All right, so that's a quick synopsis, I suppose, of the videos, the pre-class videos that you should have watched before today. Are there any questions, Alec, that have come up, or things that we should talk about, I guess, before we get into the new stuff for today?
So the only question that came in just said, what is the content of exam 2? Sorry, I'm late for the course. Yeah, we went over that right at 2 o'clock. It is on the D2L page.
Yep, so we have this wonderful, important info about exam 2 page. And we'll be, linking a few more times directly to this, but right now it's just under content, and you can see kind of weekly content, week 14, exam 2, and then there's important info about exam 2. And so, yeah, it's just chapter 11, but this page right here has lots of nice information, really spelling out kind of what exam 2 is going to look like.
And then another question is, are there any polar functions that don't have Cartesian equivalents? You can always switch to Cartesian, but a lot of times they won't be functions.
Yeah, and they quite often will look a lot more horrible.
They can be awful.
Yeah.
Polar is way easier.
Yep. Anything that looks circular-ish, and we'll see kind of my last problem in today's notes. Hopefully we get to it. We see like you get things like, four-leaf, they call them four-leaf clovers or four-leaf roses or things like this. So yeah, there's some pretty ones that are a lot simpler in polar than they are in Cartesian. Okay, great. So with this, why don't we go ahead and try one of these things. Here we have the polar axes and everything kind of given to us. And I have different radians, and kind of down here you can see I have different radiuses kind of marked out and everything. And so I'd like to go ahead and graph this polar equation, r equals 4 cosine theta. And so again, kind of just like we used to do back in our algebra days when you were first learning about how to graph in rectangular coordinates, what you did is probably make a plot here, or a table where you have different independent inputs, and then you have some dependent variable that gives you outputs. And so of course, with me seeing a cosine here, I'm thinking that it's going to be periodic, and maybe I can get the full picture just by going from 0 to 2 pi. So I think this is usually a good place to start, especially when you have lots of these sines and cosines. So let's go ahead, right, with just 2 points, it looked like a straight line. So let's kind of put in a few more points. Pi over 2, 3 pi over 2. We can kind of see what the picture is going to look like at this point, but we may want to interject a few more points as well. So let's go ahead and just leave it as this for the time being and see if we want to add a few more. So okay, if I go ahead and I plug in 0 everywhere I see a theta into my equation up here, I'm going to get 4 cosine of 0. 4 cosine of 0, that's going to be 4 times 1, that's 4. If I plug in pi over 2, I get 0. If I plug in pi, I get -1, so -1 times 4. If I plug in 3 pi over 2, I get 0, and if I plug in 2 pi, that's going to give me 1. So 4 times 1, 4. So now let's go ahead over here and start sketching these things. So first of all, I have theta equals 0. So at theta equals 0, notice we're looking in this direction right here along the positive x-axis. I haven't rotated around it at all. And we need to take 4 steps out. So that's my radius, my r value. So 1, 2, 3, 4. So this is where we are for that point there. Next up, we'd be looking at pi over 2, so straight up and down. And my point tells me to take step 0 steps out. Then if we go and we look in the pi direction, so pi is over here, pi radians off the positive x-axis, it tells me to go negative 4 steps. So I need to take this backwards. So instead of going in that direction, I'm going to go along the negative axis. So I travel backwards here 4 steps. And you can see I hit this point right here again. And so then if I do 3 pi over 2, I'm looking straight down. It tells me to take 0 steps off of the origin here. So again, I've mapped this point. So we can see only with these points that I've selected so far, I really don't get much of a picture here. And so yes, I do want to go ahead and include a few more points maybe to get a fuller picture of what's going on here. Because right now, I mean, I could connect these 2 points, it'd just be a straight line, but I think it's more than that. So let's go ahead and include something like pi over 4 and 3 pi over 4. And we could do, let's see, 5 pi over 4 and 7 pi over 4. Things like this to maybe get a fuller picture here. And here I just want to remind you, we're about to be using the square roots and things like this. In many of the web work problems, and especially when you're trying to sketch these things by hand, it's really nice to know that the square root of 2 is approximately equal to 1.4, and the square root of 3 is approximately equal to 1.7. So this will help us actually be able to, pinpoint it on our sketch. So okay, if I was to plug in pi over 4 into this, I would get 4, and cosine of pi over 4 is root 2 over 2. So there's going to be a little bit of canceling. We're going to have 2 root 2's, so that's approximately equal to 2.8. If I plug in 3 pi over 4, so 3 pi over 4, we're going to have 4 times negative root 2 over 2. Cosine of 3 pi over 4 is negative root 2 over 2. So this is going to be equal to approximately negative 2.8. If I plug in 5 pi over 4, again, we get negative 2.8, or approximately equal to that. And if I plug in 7 pi over 4, we get positive 2.8. So now let's go ahead and map these. So if I'm looking in this direction here, pi over 4 direction, I need to take 2.8 steps out from the origin. So something like this. Oops, let's go ahead and erase that. If I'm looking in the 3 pi over 4 direction, I need to actually go backwards along this 2.8 steps. So 2.8, maybe around here. If I'm looking in the 5 pi over 4 direction, again, it's telling me to go backwards 2.8. So I'm going to map this point actually again. And then finally, if I'm looking in the 7 pi over 4 direction, it tells me to go out positive 2.8. So I map this point actually again. So here, if we follow kind of all of these points, we go from here to here to here to here to here. And that's when we're going from 0 to pi. So from 0 to pi, we hit all of those points. And then we continue and we get all of the points a second time. So we hit this point again, this point again, this point again, and finally back here. So we trace out what turns out to be something that's looking awfully maybe circular or kind of elliptical. My picture's certainly not the best, but something that looks kind of like a circle, but we actually trace it out twice. And if you wanted even a better picture, right, you could start to interject some of these like pi over 6 or pi over 3 and really kind of fill this in and see that it actually is a circle in this case. All right, am I missing anything, Alec, or anything that you would like to add?
Nope, I think we had a question came in, already answered it, and I think you hit on it again anyway, that whole idea of sort of facing in one direction and then walking backward. is y, like, you know, you can end up with a -4.
Yeah, it's a little bit strange, right? Because quite often we only like radiuses to be positive, right? But here we see that actually it makes perfectly, you know, fine sense to just walk backwards. And so we do allow for negative radiuses. Okay, what is the equation in Cartesian coordinates equivalent to this polar equation? So remember, my polar equation was r equals 4 cosine theta. And remember, we had these great kind of exchange rate equations. Let me go ahead and copy them down from the notes that we had there. So we had, for instance, that r squared was equal to x squared plus y squared. We also had what r cosine theta is equal to x, and we had r sine theta is equal to y. So here we have kind of our polar equations, or our polar variables, and we want to exchange them for Cartesian, x's and y's. And so you can see we can only exchange in certain quantities, right? So I mean, if we had an r squared, we could go ahead and exchange for an x squared plus y squared. Or if we had an r cosine theta, we could go ahead and exchange it for an x. Actually, this is the one maybe that we should start with, I'm most interested in, because, right, I do have a cosine here. So if only I had an r next to it, then I could exchange that for an x. So what I would like to do is I'd like to make this r cosine theta. Now, of course, if I just put an r on the right-hand side, mathematically, I've changed things. So in order to make this mathematically valid, well, if I want to multiply by an r on the right-hand side, I should also multiply by an r on the left-hand side. And we can actually see that this has done something else good. Right now, this is lining up on the left-hand side well as well. Right, so because r squared is equal to x squared plus y squared. And on the right-hand side, we have our r cosine theta is the same thing as x. So this right here is a perfectly good Cartesian equation. Don't need to solve this for x or for y or anything like this. However, if you did go ahead and start to rearrange it, right, and kind of, there's a way that you can complete the square and all this sort of stuff. So bring this over here. Really at this point, just having x squareds and y squareds that have the same coefficient in front of them, in this case 1, we know at this point that this is going to be a circle. But actually, if you go ahead and complete the square, you can rewrite this as what? X minus 2 quantity squared plus y squared is equal to 4. And so you can see that this is actually a circle that's been shifted over in the x direction 2, and it has a radius, right? This is the r squared value, a radius of 2 as well. And so if we go back to our picture, notice that it does really look like we have a circle centered at the x value 2, y value 0, and it has a radius of 2. So actually our picture is kind of lining up with this. So this is just a little bit of kind of bonus information here. Like I said, you can actually see that it's a circle just back here when you see that the x squared and the y squared both have the same coefficient. All right, any questions on this problem?
Yeah, we just had a question about why do you need to multiply r by r? And I know you covered that quickly, but maybe hit that once more for this person.
Yeah, so multiplying by r was really, I have these certain equations that allow me to exchange r's and thetas for x's and y's. And so that's really the game, right? We have a polar equation, so we have lots of r's and thetas, and we'd like to get rid of them, and I'd love to have x's and y's, right? That's what this problem is essentially saying, is that we want Cartesian coordinates x's and y's. And so here's our various exchange rates. We can exchange an r squared for an x squared plus a y squared. We can exchange an r cosine theta for an x, or we can exchange an r sine theta for a y. So these are the possible exchanges, but sadly, right, we don't exactly have any of those exactly. However, if I multiply by an r over here, we get r cosine theta. By the way, this is not the only way to view this. This is, you know, I like these exchange rates and whatnot, and this way of thinking about it. But I've also seen students who do very well, who just write this as, they do a rewrite, and they say cosine is equal to, and you could do x divided by r. So, right, we have cosine, and so we can exchange that for x divided by r. So you could just go ahead and exchange this for x divided by r, right? And then you could maybe bring over that r to the other side, and essentially you'd get to the same place that we made it to as well, right? Now you see we have an r squared, and so r squared is the same thing as x squared plus y squared. And now we've kind of met up and we're at the same place. So this is another way that you can think about it. And again, I've had students very successfully implement this, and this is just the way that they do all their problems. So it's up to you to find a way that you really like to do them, and then stick with that.
And then somebody else asked, can you show the complete the square process?
Oh, sure. So completing the square, this is something, this is right, an old algebra technique. It's a little bit getting into the weeds with this, right? So this is not maybe the emphasis for this problem. And so if this is making you wildly unhappy while you're watching this, don't focus on it too much or anything like this. How you do the completing the square process is that, well, you want to add something to this so that you get a completed square. And there was this rule of, what is the right thing to add in order to get a perfect square. And it relies on what's next to this x value right here. Sometimes this is called b. And so you need to take this, you always need to divide it by 2, and you need to square it. So that's the rule in order to get a completed square. And there's a lot of proofs and stuff like this, and beautiful representations of why this works. But I'll just say that this is the rule. And so if you take -4, you divide it by 2, you get -2. If you square it, you get 4. And so we want to put a 4 right here. And with this, you can go ahead and verify, right, that if you take x minus 2 and you actually square it all out, right, and you do the first, the outers, the inners, the lasts, right, you FOIL it all out, right, you do get back to this. So this is the completed square x minus 2 quantity squared. Now, of course, if I just put a 4 on the left-hand side like this willy-nilly, right, I've changed things wildly. So I also need to add 4 on the right-hand side so that mathematically it's valid. And that's why the 4 is over here. So that's the process for completing the square. Okay, so why don't we go ahead and try another one of these. This is one that I usually give my students a bit of a chance to work on. So this is r equals 7 over sine theta. And I've started off by saying graph 3 points of this equation. So please take 90 seconds or so. I think this is a good exercise to plot in a few points into this and see what comes out. All right, so that's probably enough time. So you see, if you just start plugging in maybe your favorite points to plug in, for instance, oh, I did a bad job here. This is meant to be 0, and I just rewrote theta. But if you plug in things like 0 or pi or 2 pi or things like this into sine, right? Sine is 0 at all of these points. And because you're dividing by sine, well, you're dividing by 0, and that's not so great. So those won't actually give you points on the graph. So those ones we can't really draw. So if you draw, you select a few others, and I selected ones that I know they plug in well into sine. And so for instance, pi over 2, sine of pi over 2 is going to be 1. So I'd have 7 divided by 1, which is 7. And then you could choose pi over 4 and 3 pi over 4 and things like this. But if I plug in pi over 6 or 5 pi over 6 into sine, we get out 1/2. So, right, so this is 7 divided by 1/2. Of course, instead of dividing by a fraction, you could multiply by the reciprocal, and you get out 14. And likewise, at 5 pi over 6, you're also getting out 1/2 for sine. And so multiplying by 2, you get, again, 14. And here's where I realized I made it kind of, I don't have any axes here. So I'm going to go ahead and say that this is 7, and this is going to be 14. So I'm awkwardly doing, I guess, steps of 3.5 or so in order to do this. But we can see at pi over 6, we need to go out 14. And at 5 pi over 6, we need to go out 14. And at pi over 2, we need to go out 7. So something like this. So if we were to go ahead and connect these three, it seems like it is forming a straight line. It seems to be a straight line here. And so I would maybe guess, we know that kind of, if you were looking, for instance, in the 0 direction, or theta equals 0, right, you would indeed never hit that straight line. So that's why maybe the infinity's there. Or if you're looking in the pi direction, or really any multiple of these things, right, it never seems to hit this. So that's maybe why the infinities are there. So we think maybe it's a straight line, but let's go ahead and verify this, right, with part B, right? What is the equation in Cartesian coordinates equivalent to this polar one? And so again, we have r is equal to 7 divided by sine of theta. We need to use our exchange rates, right? And in particular, I see this division, maybe we don't really like the division, right? And so I could say, well, let's go ahead and multiply by sine on both sides, get rid of this division. And so I could make this as r times sine theta is equal to 7. And of course, r sine theta, that's exactly equal to y, according to our exchange rates. So we have y equals 7. You can see that this is a nice line. It seems to be at height 7. Remember, this is 7 here. So it seems to be a nice horizontal line at height 7. And so C, right, what is the shape of this curve? Well, it's a line. Which, by the way, you know, this stuff like this is pretty easy to code into web work, at least parts B and C, right? It's kind of hard. I've seen some of them that have multiple choice questions where it's kind of which of the following curves, you know, looks like 7 over sine theta. But then certainly getting into this stuff, right, what is the equivalent Cartesian equation, right? You can just give a couple text boxes here to write down this, and then maybe a drop down in order to select a line or circle or parabola or things like this. Any questions we should be thinking about, Alec?
Yeah, let me interrupt for just a second here because first of all, my internet connection is all of a sudden really unstable, so you're cutting in and out on me.
Oh, sorry to hear that.
I think it's just on my end because nobody's shown, but maybe just really quickly, participants, if you would raise your hand if you're having really glitchy audio and video. I don't see any hands going up, so I'm pretty sure it's on mine. I've got a message across my screen that I have unstable internet. So,
yeah, you know, I went out and I bought one of these Ethernet cables, and so I have because I was having some issues with my Wi-Fi here and there, and so on my desktop anyway, what I'm hosting the session with is actually hardwired.
Yeah, I've been actually working on that. The problem is my office is in the basement. I'm gonna have to drill holes in my floor. But
oh yeah.
I'm gonna try to do something like that. So the only question that's open right now is it said, would it be illegal to use cosecants if that's easier for us?
Would it be illegal to? I mean, certainly you could use cosecant. I think it's maybe it's hiding things a little bit as far as when you exchange for Cartesian equations, right? You see the sign really jumps out to you as far as what we can exchange this for. But yeah, you could use cosecants, especially in part A, if this was more convenient for you to actually plug things into.
And I would also just point out that on that second part, though, notice how you end up multiplying both sides by sine anyway. So at that point, it's probably easier if you had left it with sine instead of you'd have a, 1 over cosecant otherwise.
Yeah. All right. So let's go ahead. Here's one that's maybe a bit more full strength. This one, we're not going to be sketching so much. We're jumping right into, can you figure out what the Cartesian coordinate equivalent of this would be, and then what would the shape then be. And so again, there's some different ways that you can go about this. So if you're happy with exchanging, sine is y over r and cosine is x over r or things like this, that's completely fine. But again, when I'm looking at this, I see, well, there's this division and maybe I don't really want this division, right? Fractions aren't great if we don't need them. And so I'm tempted to go ahead and multiply through by r. So if I go ahead and I multiply through by r, we would get r sine theta minus 6 r cosine theta, right? Because you need to distribute it to each piece. And now you really see we have an r sine theta, we have an r cosine theta. So these are exactly what we can exchange for y and for x. So in this case, we get y minus 6x is equal to 8. If you wanted to, you could go ahead and rearrange this. Oops, 6x plus 8. And then that's maybe something that you really indicates to you, right? The old mx plus b sort of deal. It really indicates, hey, this is going to be a line. All right, so that's example 15. Here's something that's, again, kind of just algebraically, how can we exchange things? So consider this polar equation, and I'd like to rewrite it in Cartesian coordinates. So please, why don't I give you 60 seconds or so to go ahead and rewrite this in Cartesian. All right, so even though this one looks a little bit messy, the technique is still the same. And again, if you'd like to go ahead and figure out, just exchange, sines and cosines, for instance, by rewriting these equations, you certainly can do that. But when I see this, I think, man, I'd really like to have an r next to that sine, because then I can go ahead and take this and exchange it for a y. And likewise, I'd like to have an r next to this cosine, because then I can go ahead and exchange it for an x. And I'd also like to have an r next to this cosine, so that way I can exchange it for an x. And so really, in total, I'd like to interject 3 more r's, and these are all being multiplied together. So if I'm going to multiply 3 r's on the right-hand side, I should probably also do it on the left-hand side. And so this is going to be r to the 4th is equal to 4 times y times x squared. And of course, we know that r squared, maybe if we wanted to, we could rewrite this as just r squared times r squared. R squared is the same thing as x squared plus y squared. And there's 2 of these things, so this is just going to be quantity squared. So this right here is a perfectly fine equation that's Cartesian equivalent, right? So again, don't need to solve for x or for y or anything like that. Any questions or things that you'd like to add, Alec?
I think, again, you're kind of cutting out on me, but I think you switched the squared there accidentally on the right-hand side.
Oh, thank you.
Mm-hmm.
Y and x squared. Okay, yes, thank you. And I see that just came up in chat as well. Thank you, yep, Jacob and Nolan. Okay. So with that last page here, of course, with these things, right, instead of just doing equations, you can also do inequalities. That used to be a game that we played back in our algebra days as well. graphing inequalities. So I'm going to do this, and then I have kind of a difficult graph here just to finish the class up with. So, okay, we'd like to do inequalities, and there are, I think, 2 web work problems, at least in the learning sets, that are quite similar to this that I can recall. So give the inequalities for r and for theta, which describe the shaded region in polar coordinates. And so the first thing maybe I'm interested in is I could specify what theta values, right? What theta values do you actually intersect this region? And so notice here at theta equals 0 where I start, and maybe I'm skimming just the very bottom of this region, so I'd like to include that. Of course, if I do like, theta equals pi over 6, or theta equals pi over 4, right, my inequalities seem to be, right, it seem to be hitting this region here. Pi over 3, pi over 2, but then after that, I no longer am intersecting this region at all, right? So there's no reason I don't need to include theta values that are greater than pi over 2. So I could say right now for theta, that theta ranges between 0 and pi over 2. That's where I need to actually be plugging in our theta values. So that's this. So the theta, done. Now the r values, right? When do I really enter the region and when do I exit the region? Well, remember r values, they start off at the origin here and they kind of radiate outwards, right? So the first place where I actually enter into the region seems to be along this curve thing. And it didn't give me a whole lot of information, right? If this was maybe a quiz or exam question or something like this, there'd probably be some extra words to really specify this, what this shape is. But looking at it, I'm pretty convinced that this is just a circle, right? That this is a circle centered at the origin with a radius of 1, right? It's part of a circle, maybe only the circle between 0 and pi over 2, for instance. So, okay, I'm pretty happy thinking that this is going to be a circle, right? Circles have the equation maybe x squared plus y squared is equal to 1. If I wanted to transform this into a polar equation, well, I know x squared plus y squared is the same thing as r squared. And so if I go ahead and I take the square root on both sides, we can see that this is just going to be r equals 1. So with r equals 1, which makes a lot of sense, right? No matter which direction you're looking in, you take 1 step out. So yeah, r equals 1. That makes a little sense in hindsight. I think that maybe this is going to start off with r should be greater than or equal to 1, right? That's how I enter into this shaded region. I exit this shaded region at different points, right? So different lengths. It's not a constant radius here, but you can see that it's actually getting longer as I get a bigger and bigger theta value. And then at pi over 2, it seems like I would never actually exit. I would just kind of keep on going on forever in this direction. But the big thing is that it's a straight up and down line. So a straight up and down line at 2 here. Really the x value of 2. So there's really no restrictions on y, but the x value is 2. So same sort of game as before, I'd like to convert this into polar, right? Because I need to specify a bounds on r. And so what I'm going to do is that I'm going to go ahead and exchange. Instead of x, I'm going to put r cosine theta. So now kind of exchanging in reverse here. And well, if I want to solve r equals, right, I'm specifying an r bound in this case, I would say r is equal to 2 divided by cosine of theta. So I just divide by cosine on both sides. And this is actually quite similar to one that we had up here, right, a couple pages ago, where we had 7 divided by sine theta was a horizontal line. It's maybe not surprising that when you divide by cosine, you get a vertical line. So we can go ahead and instead of, for our upper bound here, we exit the region by 2 over cosine of theta. So that's going to be where we actually exit the region along this straight up and down line right here. So this is how we could do inequalities if we really wanted to. And you could even plug in a few points really to just make sure, you know, kind of convince yourself. But if you plug in theta equals 0 and a theta equals pi over 6 and theta equals pi over 4, right, you can kind of see these points getting farther and farther away, traveling along the straight line. All right, so those are the inequalities right there that would specify this shaded region. Let me see, Alec, are there any questions, or how's your internet doing? Well, it looks like I've lost Alec for a second anyway. Any questions, guys?
Can you hear me?
Yep, I can hear you, Alec.
Okay, it's again kind of cutting it out. Did you ask me a question?
No, just was checking and seeing how people were doing. So it looks like I couldn't see any questions, so must be relatively good.
No questions.
Right. So one more, this is just kind of the extreme side. There's a few kind of harder web work questions in the learning sets, which, you know, there's a wide breadth of content in the learning sections, but here we have r equals 6 sine of 3 theta, and this is something that we want to graph. And so let's go ahead and work on this one together. We might get done with class a bit early. We'll see. This one does take a little bit of time. So we're going to have different theta values, different r values. And again, we could go from 0 to 2 pi. The only problem is that you can see that when you put in different theta values, right, these actually get multiplied by 3. So everything's going to be happening a bit faster, right, because you have this going, right, and being multiplied by 3. This is changing really the period for the sine function. It's actually maybe a good thing to start off with, since things are happening a bit faster. Let's just see what the picture looks like if we were to go 0 to pi, right? And so we could start interjecting, you know, maybe pi over 2 and pi over 4 and 3 pi over 4, things like this. But then we can, oops, my iPad's a little bit slow here. I've caught the bad internet.
Yeah, I gave it to you. Sorry.
Yeah. Yeah, my iPad looks different than this. Let me see if I try to change apps. Sometimes this works. You know, I mirror the iPad in class, and sometimes there's a little bit of a connection issue. I'm trying to turn it off and turn it back on. Oh, now I'm kicked, and it's coming back. And share screen. I have hope. Or this might just be a really awkward ending to the class. One of the two. All right, so this is what my iPad looks like. I'm happy so far, anyway. But like I said, because we're multiplying by 3, notice that if I did something like pi over 6, when you multiply that by 3, right, it becomes kind of like a theta value of pi over 2, right? So you could actually even do a lot more things. You could do like pi over 12, for instance. You could input that because, again, you're multiplying by 3. You know the sign. Remember, you don't have to do sine of pi over 12, but when you multiply it by 3, it's going to be sine of pi over 4. And this we actually know on the unit circle. So you can actually put a lot of detail into this. But again, it's not clear at this point that you need such detail. So why don't we start off with these values here, and then we'll see if we need a bit more. So if I plug in things like 0 into sine, I get 0. Or if I plug in pi into sine, I get 0. If I plug in pi over 2, well, when you multiply that by 3, sorry, you're going to get 3 pi over 2. So this is actually going to be -1 times the 6 will be -6 here. When you plug in something like pi over 4, again, you multiply that theta value by 3, you're going to get 3 pi over 4. And the sine value at 3 pi over 4 is going to be √2 over 2. So you're going to have 6 √2 over 2. So again, things are going to cancel a little bit. You're going to have 3 times 1.4. So this is going to be approximately equal to 4.2. If you were to plug in something like 3 pi over 4, again, when you multiply it by 3, you're going to get 9 pi over 4. This one takes a little bit, right? You actually go all the way around the circle and then some, and you're actually going to end up with the positive √2 over 2 again. And so this is going to be equal to 4.2. And so we could go ahead and start plotting at least these ones here. So if I plug in 0, I get 0. If I look in the pi over 4 direction, I need to take a step 4.2 out. If I take a look in the pi over 2 direction. So straight up and down, I need to go -6. So -6, that's all the way down here. So backwards. If I'm looking in the 3 pi over 4 direction, so in this direction, I need to go out 4.2. So 1, 2, 3, 4, and change. And if I'm looking in the pi direction, I need to go out 0. So with this right here, we're not really getting quite the full picture yet, as you can probably imagine. So we need to include some other values. So let's maybe include something like pi over 6. This is a good one because when you multiply it by 3, you get sine of pi over 2. And sine of pi over 2, this is kind of, 1. This is the biggest it's going to be. So you really see that it's 6. So in this direction, pi over 6, it would go out by 6. But like I said, you could also plug in things like pi over 12. And this is going to give you the 4.2 again. So now you can start to see that if you were just to graph the 0, and then the pi over 12, then the pi over 6, then the pi over 4, then the pi over 2, you're starting to get something like this. After that, if you continue, you get a few negative 4.2s and stuff like this. You're actually going to go backwards here, right? So these are all going to be negative, and you get something that looks like this. And then finally, just kind of spoiling the surprise here because I'm hoping that you saw, we did this first one in quite a lot of detail, which I'll just shade in right here. But this is actually going to be a 3-leaf rose or 3-leaf clover, if you'd like, with this 6 sine of 3 theta. And actually, so before class here, I should have done one more thing as well, but I went ahead and I graphed on Desmos. Let's see if this loads. Oh, but it's just gone now. Well, fine. It doesn't take that much longer, even though I did have some more input here. But if you do r equals the 6, and this is maybe a good exercise anyway to see that you can just type these things in, but 6 sine of 3, and then you just spell out the word theta. And we can close parentheses if you'd like. But you can see that, yes, we get this 3-leaf clover, essentially. And if you want to, you could parameterize this and you can actually see it. It's nice. It's very satisfying. I wish that this would have loaded correctly, but it's very satisfying to watch the dot kind of travel along this. So maybe at the beginning of next class video, because again, we do have a couple days dedicated to 10.3. Maybe I can start with that, where you get to see the actual dot, going around this 3-leaf clover thing. Okay, so that's the last problem and what I really wanted to go over here. Of course, we're going to be getting into the calculus of these things coming up next. So 10.2 is the calculus of parametrized curves. 10.4 is going to be the calculus for polar equations, and so we'll be able to talk about slopes of tangent lines. We'll even be able to calculate out the area for maybe one of these leaves in the 3-leaf clover or the 4-leaf clover, anything like this. So we're going to be doing some calculus coming up next. So I do apologize that we haven't had very much calculus here in this calculus class, but I assure you that it is coming. So yeah, I have a question here. Can you add more leaves to the design? What would it take to have this change in the function? So this is really something nice for Desmos. Let me jump over here back to Desmos. iPad's behaving a little bit slowly here. And then kind of the natural guess for things is what happens if you were to change, this 3 inside of here. So this would be a good hypothesis. So why don't we go ahead and maybe first kind of change it, right? If we don't have anything, we can see that it turns into a circle here. If I do a 2, we can actually see we have one of these 4-leaf clovers or 4-leaf roses sort of deal. We saw, of course, what 3 looks like. You can see 4 gets very extreme. 5. So you can maybe come up with a pattern, right, based on whether it's even or odd, how these things are going. So you can go 6, 7, Oh, wow, I did 88. Anyway, so yeah, here's where you can kind of experiment with. Desmos is great for this as far as how do you get more leaves. And of course, that 3, we saw the 3 leaves, and so it's kind of was a natural guess anyway to change that number there. All right, so I guess that's it for today. Out a bit early. If there's any questions, we'll stick around for another 5 minutes or so, so ask away. Otherwise, thank you guys for joining, and we'll see you next time.